Energy exists in many different forms. It can change from one form to another and can be moved about, but is never used up or lost, made or destroyed. The total amount of energy stays the same. That's the law of conservation of energy. As you watch the next clip, note down as many different forms of energy as you can and how they change from one form to another.
We live our lives surrounded by energy. It's easy to see the effects of energy, but it's much more difficult to say exactly what energy is. Yet it's energy that is powering our everyday lives and shaping our civilization. But how we came to understand energy in all its complexity and how we put it to work in our everyday lives is one of the greatest detective stories in the history of science. So, what precisely is energy? How can we define something that appears in so many different forms? Sometimes it's locked away as chemical energy. You have to burn diesel to release its energy. That reaction can power machines like diesel generators, which convert mechanical energy into a more convenient form, electrical energy. A similar kind of chemical reaction is happening inside us when we exert some muscular energy. Sound is also a form of energy transmitted by molecular vibrations that can travel, for example, through air. But where does energy come from, and where does it go to? Well, sometimes we can see it being handed on from one object to another. The story of how all these energy conversions and transfers take place is without a beginning or an end, but the total energy in the system is always constant, always conserved. This swing boat has two types of mechanical energy: kinetic energy from its motion and gravitational energy due to the pull of gravity. At the extreme end of each swing, it's all gravitational. As it passes through its lowest point, its kinetic energy is at a maximum. In between, one form is gradually converted to the other, but at any time the sum of the two is always constant. But in practice, this interconversion of energy isn't 100% efficient. To keep the swing boat moving, there has to be a continual supply of energy. Cut off the supply and the boat slows down. So if the energy can't be destroyed, where has it gone to? A clue might come from the fact that the bearings and the brakes are hot.
So you might have spotted chemical energy stored in fuel, food, muscles or batteries, electrical energy that can travel in wires, radiant energy such as light, infrared or ultraviolet, and sound energy. We also saw kinetic energy in the things that were moving, potential or gravitational energy stored in the objects when they are lifted, and heat or thermal energy. The clip also showed how energy could change from one form to another. The kinetic energy of the giant swing becomes extra potential energy at the top of its swing, and the potential energy becomes kinetic energy again at the bottom. The energy stored in the fuel powers the generators, which work the lights and motors. If you didn't quite get that, here's another clip about energy transfer.
Now, what energy transfers are going on here?
The bucket fills with water. High up, it has potential energy. When it's heavy enough, it starts to fall. As it comes down, the potential energy transfers to movement or kinetic energy in the wheel. As the wheel turns, kinetic energy is transferred to this dynamo. It also produces sound and a bit of heat too. The dynamo transfers kinetic energy into electricity. And the radio transfers the electricity to sound and some heat.
So the whole system is mainly a transfer of potential energy and kinetic energy. Now, only 6% of the potential energy the bucket had is going to the radio. So it's not very efficient, but it's very useful.
A good way of showing how energy changes is with an energy flow diagram. If you put the energy converting process, like an electric cooker, in a box, you can show the energy input coming in from one side and the energy output going out on the other side. In the case of the electric cooker, the energy input is electricity and the energy output is heat and some light. How could you extend this flow diagram backwards? What comes before the electric cooker? The energy conversion process that produces the electricity for the cooker is the power station. It uses chemical energy from coal, oil, gas or nuclear energy, or the power of falling water. Look out for some more energy flow diagrams in this next clip. What are the energy flows involved when squash player Kathy hits the ball against the wall?
The first link in our energy trail is from the moving squash ball to Cassie. Cassie got her energy from food, and that came from plants. Plants store energy from sunlight, so the source of the energy in the moving squash ball is the sun.
Here's another example.
For the bike to move, we needed to put in some fuel. There's masses of energy stored in petrol. The bike transfers the stored energy in the petrol into active energy. The bike moves and the mud flies. Some of the energy is transferred into sound. After the race, parts of the bike are still hot, and that heat will be transferred into the air as it cools.
Let's go back to the power station and see how good it is at converting energy from one form to another.
Our main use of coal is to burn it in power stations like this one, Drax in North Yorkshire. The energy in the coal is used to generate electricity. The electricity is delivered to where it's needed along a grid of cables. Every day, Drax consumes 33 trainloads of coal. That's a bag of coal burnt in the time it takes to snap your fingers. The amount of energy transferred at power stations is awe-inspiring.
This one turbine generates enough electricity for a city the size of Leeds.
And there are 6 of them at Drax, enough for 1/10 of our electricity. But there is a drawback. It comes as a surprise to most people to learn that most of the energy that comes into the power station goes to waste. Only about 35% of the energy that's released from burning coal actually goes into the electrical cables that supply our homes, schools and factories. The other 65% ends up as waste heat. That's not because the designers and the engineers haven't done their job well. Apart from being the largest, this is one of the cleanest and most efficient coal-fired power stations in Europe.
The clip said that Drax was 35% efficient. What does that mean? All the energy stored in the coal is converted into some other form of energy. No energy is lost. It's just that by the time the coal has been burned, the water heated, the turbines and generators turned, only 35% of the original energy is transferred to the consumer as useful electricity. 65% is wasted as heat that goes into the surroundings. So the efficiency of an energy conversion process is the proportion of energy input that is made available as useful energy output. As a fraction, efficiency is useful energy output divided by energy input, times 100 if you want it as a percentage. Efficiency also depends on what you mean by useful energy and wasted energy. A normal electric light bulb produces 10% light energy and 90% heat energy. So as a light, which is what we want, it's a miserable 10% efficient. If we wanted it as a heater, it would be a fantastic 90% efficient. Here's a story about how the BBC uses the heat wasted from generating power.
Television Centre, the headquarters of the BBC in West London, is rather like an airport or a hospital in that it's a building that never sleeps. It's any time of the day or night. There are people here working. Over 5,000 people work in this building. They need heat and ventilation. And then, of course, there's food. People need to eat, and these kitchens provide over 2,000 meals every day. And this building's more like a small town in terms of the energy it uses. The energy to keep all of these people warm in the winter and cool in the summer costs another £250,000 in heating and air conditioning. But that's about to change. The BBC is the latest in a growing number of companies which have decided that the best way to provide all their energy is to bring the power station to where the energy is needed.
Inside this box is a mini power station. At this end is a jet engine fueled by gas. Just like with a normal power station, it's the engine that turns the generator, and the generator that actually makes electricity. That's here at this end. But that's where the similarities with a normal power station stop.
At the back of the machine is a special pump. It takes all of the heat that might otherwise go to waste and uses it to provide warmth, hot water and air conditioning for the whole building. The system is called Combined Heat and Power, or CHP. There are no cooling towers here. Much more of the energy is used. There's even some heat to spare, and that could be piped into these houses nearby. By pensioning off the old boilers, the BBC will be cutting its energy bill almost in half.
But the best thing is that 80% of the energy that comes into the building in the gas pipes is turned by this machine into usable energy. And remember that in a coal-fired power station, 35% is considered good going.
So with a combined heat and power plant, about 35% of the input energy goes into generating useful electrical power, and another 45% goes to making useful heat, now leaving only 20% wasted, an overall efficiency of around 80%. Remember, energy transfers usually produce more than one form of output energy, not just the useful output we're looking for, because overall, no energy is lost or gained by the transfer. There's more about energy transfer in the physics section of the higher tier programme. That's the end of this section on energy transfer. Now, let's see what we mean by work, power and energy. When you lift a weight, you do some work. The energy transferred from the weightlifter to the weights can be measured by the work done. The work done lifting the weights depends on the size of the force and the distance the force moves. There's an equation for this, which is work done equals force times distance. The unit of measurement for energy and work done is the joule. The work done in joules equals the force in newtons times the distance in metres. When the weightlifter lifts the weight, he's using his muscles to transfer energy from the food into extra potential energy in the weights when they're off the ground. The force he uses is equal to the pull of gravity on the weights. That's the mass in kilograms times the gravitational field strength, G. The distance he moves the weights is the height lifted in metres. So the work the weightlifter does, the energy transferred, is equal to the mass of the weights times G times the height lifted. There's more about work, power and energy in the physics section of the higher tier programme. That's the end of work, power and energy.